topic today is going to be quite futuristic. Some of the things, probably most of the things I will present will not be found in any voice textbook, but there's a combination of things that are classically well known, but also looking at things that have only been discovered about the universe in very recent years. So if I may share my screen. So the topic is intelligence and information that is carried by light and sound. That's what we're going to be talking about today, light and sound and how it carries intelligence and information. So I first declare no conflicts of interest of any type for this presentation. So we might ask, what relations exist between these following words: intelligence, organization, information, and entropy, a word that maybe some of you are not that familiar with. Intelligence is defined as the ability to learn, to understand, to deal with never or new or trying situations, or to organize. And this definition is after Webster. Organization itself is the arrangement of various elements into a whole of interdependent parts. Information is basically news, facts, and data. And then entropy is the degradation of matter and energy in the universe to an ultimate state of inert uniformity. Think about that. That's the hardest one to get clear in our head. A drift towards an ultimate state of inert uniformity. So everything looks the same and will never change, basically. That would be kind of the extreme case of entropy. So the first thing I want to talk about is the relationship between information and probability. This came from a famous engineer by the name of Nyquist, pre-World War II in the 1920s, and then later was further developed by Shannon in the 1940s. Both of these people were at Bell Telephone Laboratories, which was once the most prestigious place to go and study science, and many Nobel laureates came from Bell Laboratories. I had the pleasure of being there for 2 summers, and so I got to know the layout of the place in Murray Hill, New Jersey, but I never met with giants of this type that we are talking about here. Nyquist, you may have heard that name. There's a Nyquist theorem that says that when you sample a signal, if you want to preserve up to a certain frequency, then you have to sample at twice that frequency. That is called now the Nyquist theorem. But Shannon is known for his formula where he relates the probability of something happening to the information that's necessary to express that probability and to transfer it to another place on some type of channel of information. And here, pardon the mathematics, but H is, well, X, let's start with X. X is an event. And then we're saying what probability is there for that event to occur, and that it's P of X. And then the information, H of X, either gained or necessary to describe that event, is then related to the probability as minus the logarithm to base 2 of that probability. And what are the units of information? It's in bits. And some of you may know what bit stands for. It's a binary digit. And all computers deal with these binary digits. They're either 0 or 1. What this particular formula says, that high probability yields a low information. In other words, if there's a high probability that something happens, we're not interested in it because it happens all the time. If I say, what's the probability of the sun rising tomorrow morning? I'd say that's 100% probability Therefore, there's no information. We already know all of that. But low probability leads high information. So if somebody were to say, hey, tomorrow the sun is not going to rise, whoa, we would all be alarmed by that. And that would say, be on every television station because it's so much information that we need to know about. So you can actually plot this formula here with a little, 5 lines of MATLAB code will do that for you. And so here on the vertical axis, I show information in bits, binary digits, and the probability of something occurring on the x-axis. So let's take an example. If we were to take a coin, and the coin has heads on both sides, okay, and then we flip it, and the probability of heads occurring is 100%. It's a 1. Okay, and so you can see where that lies on the graph. Right here, if the probability is 1, then the information gained from that is 0. We know exactly that there's always going to be a head. But now let's take a coin where you have a head and a tail. So then the probability of you getting it right is 50%, or 0.5. Everything is normalized to 1 here in terms of probability. Now, the interesting thing there, now it says that you need 1 bit of information to understand that occurrence or transmit it to somebody else. Again, what's a bit? It's either a 0 or a 1. So that's pretty clear. Now let's take an event that has a lower probability, such like rolling a die. And if there are 6 sides to the die, we might ask, what's the probability of rolling a 1? And the probability is 1/6, because all sides look similar, and we expect there to be equal probability that it'll land with one of the numbers. So the probability of 1/6 is about 0.2, a little less than 0.2. So if you go up on the curve from a little under 0.2, then it says that you need between 2 and 3 bits of information to accurately describe that event. Okay, so instead of just having a 0, 1, you need probably a 0, a 1, a 0, or 1, 1, or at least you need to have 2 numbers behind each other that are zeros and ones. Okay, so that's the relationship between information and probability that Shannon came up with. Following up on that, we might also discuss what is known as information entropy. That's the uncertainty in the information that we're sending to someone or giving to someone. So let's assume you have a set of occurrences or events that are described by X. Could be just one of them, but we could have multiple occurrences over a period of time. And then the uncertainty, also known now as entropy of those occurrences, is minus the sum over all the occurrences over all X. And then in brackets, you have an interesting kind of a multiplication. It's P of X, the probability of X occurring, times the negative of the information. And that negative sign is very important because that tells you that there is a sort of an inverse relationship between information and uncertainty, okay? But because of this P of X in there and this multiplication, entropy can rise and fall with information. So I've plotted another curve here with MATLAB where we show the entropy or the uncertainty of an event happening against the information that is transmitted in bits. And it maximizes itself between 1 and 2 bits. To me, that is enormously important. So if we're trying to pass information to people, and the only way we can express it is in 2 possibilities, and that's all you get with 1 to 2 bits, then we would always have to say things are true or false. Things are black or white. I'm either a Republican or a Democrat, or things are high and low. We can't get anything in between. And so the amount of uncertainty is quite great if we were to communicate only with binary kinds of information, either this way or that way. But if you want more precision and more certainty in your information, you have to take more bits. And as you go up here between 2 and 3 and 4 and 5, you can see there's an inverse relationship between the uncertainty or entropy that you of the signal that you pass on to somebody and the number of bits required. This may not seem all that important to you, but the Shannon formula and all of this work that was done about transmitting information over links and wires and so forth, this was earth-shaking to many people. No one had ever really made that connection before between certainty and transmission and the amount of information that you need to describe it. Now, just very recently, and I refer you to Physics Review Letters, 2013, a person by the name of Wissner-Gross, and he has a TED Talk that you can look up, by the way, wants to quantify intelligence. Okay, well, we quantify intelligence in schools by an IQ, an intelligence quotient, and that's a number somewhere between 80 and 150, whatever. But that's a very, very unprecise and unusable kind of a number. And Wissner-Gross argues that intelligence, which is in fact hard to quantify, can be reduced to the maximization of one's options. Wow, that is a statement. Let me read it again. Intelligence can be reduced to the maximizing of one's options. So in the future, if you're thinking of what you're going to do, if you think in a way where you give multiple possibilities, as many options as possible, you will become a very intelligent individual in carrying out the functions that you need to carry out. So Wissner-Gross gives an equation, and this is a crazy one. He uses the letter F for what's called causal entropic forces. Causal entropic forces, that's the equivalent for him of intelligence. Okay, and he says that's related to a constant, which he calls T. It's supposed to be like temperature, but I never saw the correlation between that and temperature. Just think of it as a proportionality constant. But then what's really important is this quantity here. The upside down delta is the statement for divergence. Divergence. And so, and S is the symbol for entropy or the disorder. So if you have a universe where basically you can create as much variety or much divergence, if you will, of organization, then you've created the greatest intelligence in the system. If everything goes towards one kind of an entropy, for example, everything being equal, all the particles have the same energy and so forth, then you don't have much of a possibility of increasing the intelligence of the universe. So once again, as it says below here, if the entropy S of a system is diverging, becomes more diverse, then intelligence is increased. All right, we can talk about that in the question and answer if you hung up on it. We can ask the simple question, does a rock have intelligence? The answer is yes, it does, because it has molecular organization, and information can therefore be gleaned from it, from that organization. But here's the kicker, left in isolation, it will eventually disintegrate and lose all its organizational structure, and therefore its intelligence and its entropy is maximized, okay? Now, there are people, even in the last 4 years, who have challenged Wissner-Gross's theory and say this, that causal entropy forces, which is the F in the equation that we had, do not explain intelligent behavior from first principles. The theory cannot explain how an intelligent agent, and that's what you apparently need, evolved in the first place. I mean, given a universe, say without any intelligence, just matter and energy unorganized, what is the agent that allows it then to evolve with this changing in multiple entropies that exist? So that's a valid question, and it is for me. And so therefore, I don't buy into this lock, stock, and barrel. Models of the universe that incorporate causal entropy are more likely to come up with a universe that contains intelligent observers. Ha, that is us, basically. So it comes right back to you need some source of intelligence to determine how intelligence increases or order increases in the universe. So I'm going now away from physics to a little bit of metaphysics. And in my talk here, probably 80 to 90% of it is real physics that has validity based upon it. But the other 10, 20% are my beliefs, and they're my spiritual beliefs. I believe that a reservoir of intelligence in the universe is a fundamental reservoir, as fundamental as matter and energy. And this is the diagram that I came up with that. Every physicist will agree that there are two reservoirs, rest matter and energy. And thanks to Albert Einstein, we know what the relationship between the two is. Rest mass can be totally converted to energy, and energy back to rest mass. We don't yet know the formula, unless Wissner-Gross is the formula, between intelligence and rest matter and energy. How do they relate? I believe that intelligence existed forever, was never created nor destroyed, and that we have access to pieces of it if we have the proper means to get there. And of course, rest matter and energy have also never been created nor can be totally destroyed. So let me talk about creation and communication. Creation then is the use of intelligence to organize or reorganize matter and energy. Communication is the transfer of intelligence with matter and energy. And we're going to get more and more into the communication part, because when we speak or when we turn on light, we actually are the agent for moving intelligence from one place to the other. There's the second law of thermodynamics, which is no longer challenged, and it's been around for a long, long time, ever since James Clerk Maxwell. And it says this, that in isolation, a system of matter and energy will lose its organization even though its total energy is conserved. You may have no loss of mass and no loss of energy, but if you leave the system in isolation, it will lose its organization and will never gain it back. Entropy is a property of the system that cannot reverse itself in isolation. The trend is always toward what we call thermodynamic equilibrium, which means greater entropy and less organization. I now show you a picture that I loved when I took thermodynamics, and it's called Maxwell's demon. I like to think of it as more Maxwell's angel, because it is so beautiful in terms of altering organization. So let's see what you see in front of you here. You have two boxes together, and there's a partition, a trap door between them. And little Maxwell's demon sits on top of that, and he wants to organize this material so that all the blue is on one side and all the red is on the other. So with his or her intelligence, the trap door is opened to let the red particles go from left to right, and every time a blue particle comes in the other direction, that's allowed to go through in the other way. And before long, you have all the blues on the left and all the right, the red on the right. Now, the energy hasn't changed, the mass hasn't changed. What has changed is the organization or the entropy, and that has been lowered. So entropy, remember, is disorder in the system. And if it's lowered, then there's more organization. Now, here's the kicker. Supposing this little demon or angel is going to go away now, never comes back, but leaves the trapdoor open. Okay, if it leaves the trapdoor open, then soon an equal number of red will go to the left, an equal number of blue will go to right, and you're right back to the original state. But the important thing is, by itself, this will never reverse. You can wait for a gazillion of years, and never will that system reorganize itself as it is on the right without intelligence being introduced. Another example of that is if you drop a cup and it bursts into dozens of pieces. Without input of intelligence, the cup will never return to its original organization. I mentioned my wife, Kathy, here. We sometimes break our plates and cups in the kitchen. But she loves some of them so much that she wants it back to normal. And so she takes an enormous amount of time with glue and her intelligence of what that cup looked like to begin with to put it back together. You see, that's what it needs. Somebody needs to know what that cup looked like originally. Otherwise, you cannot take the pieces and expect them to go back. And over time, if the intelligence is there, never, ever will that cup reorganize itself. Work and energy, work is in fact energy transfer. The act of increasing the level of energy of a given system is called work. But work can also be the process of transferring energy into a system to increase the level of entropy or increase the order. And that's what we've just seen in the two examples given. That brings us to light and sound. Light and sound are important carriers of intelligence for humans and animals. They facilitate organization, restoration, learning, healing, and change of entropy. I'm going to take a moment and lead the discussion about light and sound with a song. This is a song called Lead Kindly Light. I got to give you a little background to it because that makes it so important. First of all, in Latin languages, this would be called Lux Benigna, or kindly light. A person by the name of John Newman took a boat trip in the Mediterranean. He went from Palermo all the way to Marseille, and probably on a boat that was not all that stable and nice. And most of the trip was in the dark at night. And it turned out that when the sun finally came up and he could see the ocean and he could see where he was relative to everything else, he became very healed because he was actually also very sick on this trip. And so he wrote this poem, Lead Kindly Light. And it was then set to music by John Dykes, also a British person, who wrote other words to Lux Benigna. If you don't mind, I'm going to sit down at the piano here and play that song for you and sing it for you, and you can follow along. Lead kindly light amid the encircling gloom. Lead thou me on. The night is dark and I am far from home. Lead thou me on. Keep thou my feet. I do not ask to see the distant scene. One step enough for me. One more verse. So long my power hath blessed me, sure it still will lead me on. O'er moor and fen, o'er crag and torrent, till the night is gone. And with the morn, those angel faces smile, which I have loved long since and lost a while. Okay, so we can all be lighthouses and foghorns, basically, in our society with vision and speech. If the sky is clear and you can see a far distance, then lighthouses will guide us. And if it's foggy or dark, we can also express our feelings with something equivalent to a foghorn, which is our voice. Now I'm going to talk about light and sound as waves. Both are repeated wiggles in time and space. For light, it's bundles of energy known as photons. For sound, it is basically very complicated, either sinusoidal or sometimes very complex waves. But they're all basically wiggles, and they move from one place to the other. And about the movement, sound waves need an atmosphere to travel. We also call that traveling propagate. And sound propagates at 767 miles per hour in air on Earth. If you want to relate that speed to something that you're more familiar with, you can go on a freeway with your car at 70 to 80 miles an hour. So that is 1/10, basically, of the speed of sound. Light waves, on the other hand, can travel or propagate through free space. They don't need any atmosphere at all. And, they travel at 671 million miles per hour in a vacuum. If they're in a medium like water or something else, they travel a little less than that. But notice here that is almost 1 million times faster for the movement of light than the movement of sound, at least on the Earth here that we're on. So our physical sensory systems, and we have 5 senses: vision, hearing, taste, smell, and touch. They pick up only a tiny fraction of the waves that are around us. As you're sitting right now in your kitchen or your living room or wherever in your office, there are literally hundreds, if not thousands, of waves that are going around you and through you all day long. You have no clue that they're there because we are limited in our decoding of information or intelligence from these waves. If we could decode them all, we would be unbelievably informed about everything that goes on in the universe. And so if we can pick up any of these waves, we need to be tuned to a specific carrier signal, just like dialing in a radio station. If you go to an AM station and you put in something like a 107 kilohertz or something like that, or an FM station with a different number, what you're doing is you're basically setting up your radio to receive a carrier frequency. You will never hear or see that carrier frequency, but it needs to be there so you can tune to it, because the information you get is how you modulate that signal, not the carrier itself. So let's look a moment for what the spectrum of sound frequencies are and how much of that we can receive. So here we have 4 classes: infrasonic, sonic, ultrasonic, and hypersonic. And below that are the frequencies in scientific notation. So 10 to the 1 means 10 hertz, 10 to the squared means 100 hertz, 10 to the third means 1,000, and 10 to the fourth is 10,000. So what we hear, if we have as good a hearing as we can as humans, is from 20 hertz to about 20,000 hertz. We call that the sonic part of the whole spectrum, and because that is what we as humans hear. But that's not necessarily what other species hear. In the infrasonic region, which is red here, 0 to about 20 hertz, elephants can communicate rather well there. In fact, they communicate somewhere around 15 or 16 hertz. And that's been shown to be true because in Africa, sometimes airplanes can fly over the top and they see a bundle of elephants here, and then several miles apart, another cluster of elephants. And they're so far apart that they can't even see each other because of the curvature of the earth. But what happens is when one group begins to move or do something, the other one follows, synchronizes, and they are able to talk to each other at those very low frequencies. And in the ultrasonic range, we have also species like rats and mice and bats that produce frequencies much higher than we can, and certainly higher than we can receive. Not much to be said about the hypersonic range here. I'm not so sure if any species ever gets to that point, because 10 to the 9th is already a billion hertz, and nothing can produce that kind of a frequency in terms of humans and animals. Now, let's get to the spectrum of electromagnetic frequencies, and this is even more astounding, is how little we pick up. Here we have the whole spectrum, and I'm going to go from right to left here. They're the long radio waves, and again, in scientific notation, you can see here 10 to the 8th, and that is basically in meters. See, wavelength in meters. So this is very, very, very high wavelength, long wavelength. Then we get to the spectrum for radio waves, and there we have the amplitude modulation, the frequency modulation. Amplitude modulation on your radio set has a carrier of about 1 megahertz, a million hertz. The FM channels have roughly a carrier frequency of 100 times that, or 100 megahertz. After that, we get into the microwave frequencies. And after that, we get into infrared frequencies. And again, none of this, all the way from the right to here, we have any clue about in terms of receiving the information that is passed along with these waves. We have one little slip, which is called the visible spectrum, which has a very small range of wavelengths. This is in nanometers here, from 400 to 700. And that's all we can pick up. And that goes from our ultraviolet to infrared, basically the spectrum of a rainbow. Above that, we have the ultraviolet frequencies, and we are aware of those, but always too late. Because if we go out and we burn in the sun, we only know that we're burned after we've been burned. While we're receiving these ultraviolet rays, we have no sensors, no receptors for them whatsoever. And so they attack our molecular structure in our skin, but we don't feel a single thing. Furthermore, there are X-rays, and we can have our foot X-rayed and never sense anything about the waves that are going through our leg or our hand or wherever. And then finally, gamma rays, which are the highest energy and the highest frequency. So once again, electromagnetic waves are all around us, and there are so many different ones, and we pick up a very tiny proportion of that. Now, the information that we get on the waves that we can receive is coded by modulation. Again, I should say it's not the carrier that is the information, but the carrier carries the information. And however you modulate that signal, that will be the music or the speech that is received. And again, if it's amplitude modulation, then the amplitudes of successive cycles will increase and decrease. And that signal of how the amplitude changes is in fact the information. But if you frequency modulate, then you leave the amplitude the same, and then you can increase or decrease slightly the frequencies around the carrier frequency, and that is also then the information that's passed on. There's something very important about coherent versus incoherent systems, both in sound and in light. Many lasers that we now can produce and use can have coherent light. Coherent means that they are phase locked together. When one goes up, the other goes up. When one goes down, the other goes down. And that's easy to modulate and put a signal on. But incoherent light, which is basically either an LED that is not designed with coherence, or it's light from the sun. And incoherent light is difficult to modulate because you may have different frequencies and different phases and different amplitudes and different directions, and they all add together and it becomes a mess. So it's not easy to use incoherence when you're trying to modulate and send signals. That takes me to the Carrier-Modulation principle, and that is outlined in the book that Kitty Verdolini, Abbott, and I wrote back in 2012, Vocalization, the Science and Practice of Voice Habilitation. And we make it fairly clear in there that the carrier frequency should be at least 10 times greater than the modulation frequencies. Okay, did you get that? So if what in voice is the carrier? The carrier is the fundamental frequency. Okay, we don't have anything lower than that. So the fundamental frequency should be established, and it should be at least 10 times greater than any modulation that you put on there. And the modulation may be vibrato, it may be tremor, it may be changes in vowel, and whatever. But that's the message that's imposed on the carrier or the fundamental frequency. Also, we point out that prosody is a very friendly modulation, and that should be mastered first before we modulate the signal with anything else. Articulation, on the other hand, especially articulation with unvoiced segments, is much less friendly. Why? Because it interrupts the carrier. It shuts it down for a moment. If you go from a vowel to p, or anything else, you shut down the carrier, then you have to bring it up again. And that in itself is not a simple thing to keep the modulations clear. So when waves are moving in many directions simultaneously and they're combined together, stationary or moving images are created. These images can take the shape of physical or biological creations. And physical matter may not even be present, but our sensory system perceives it as organized matter and energy, and therefore it has intelligence, and we gain that intelligence from the signal. A good example is a hologram. A hologram is a creation with light and information. There's no matter at all in that individual that we see there, but intelligence alone was used to create an image with light, or it can also be done with sound. And in our world today, this is known as simulation. And in the spiritual world, that might be called spiritual creation. Creation before you use a whole lot of matter and energy, but you begin to use your intelligence first, and then you apply matter and energy later. How do we see sound or hear light? I give you an example of something, and I credit my good friend Brad Story at the University of Arizona for this. He used his tube talker to produce a sentence. And the sentence is, "I am the light of the world." And I hope that it comes through if I have you hear it.
I am the light of the world. I am the light of the world.
The important thing that I want to point out about this, this is done with simulation. This voice has never existed anywhere in the universe before. Okay, it's not associated with any human being, and it furthermore was not created with matter and energy. It was created only with physical law, which is basically intelligence. And the spectrogram that you see goes right with it, and you've all seen spectrograms. So we see, for example, that it's coherent sound because all the harmonics, which are the horizontal lines, are basically in phase with each other, and so, or they at least move together, and you see the form and structure of the yellow bands on top of it. And so here we can create either visually or auditorily something that has never been before in the universe, just with knowing the physical law and having the intelligence to do so. So simulation is building or creating without rest matter. Only intelligence and a carrier are needed. And it is basically physical law executed mathematically. A little bit about disorder in communication. We often hear these words now when we listen to the news: misinformation, disinformation, miscommunication, and so forth. Let me give you the best definitions I can find. Misinformation is incorrect information, but not necessarily with an intent to deceive or confound or lie. Disinformation, on the other hand, is information that's intended for deception and has a bias, and unfortunately, it's all over the media today. Miscommunication is basically a breakdown of a carrier or an additive noise that is bigger than the modulation that we intended it to be. Disinformation is a form of entropy, in communication. And I think you know now, I'll mention again, entropy is a measure of disorder of a system. And information is not necessarily intelligence or truth. And in red here, this is a little bit tongue-in-cheek, but today I see much information, more than I can handle, way too much information. I see considerable amount of knowledge, but I see not very much wisdom. And wisdom is basically the application of knowledge towards something which is good and which builds. A little bit about human vocalization today. Our vocalization is mainly in the context of speech, but there's a problem associated with that. It involves little or no calling over distances anymore, and our larynx was designed primarily for not only short distance communication, but also long distance calling. And add to that the fact that it is assisted more and more by amplification. And what's the consequence of that? I call it the speech-only problem. Speech invites a low fundamental frequency for phonemic clarity. If you have too high a fundamental frequency, then the carrier gets mixed up with the modulation, and then it's not clear anymore. And as I said before, if you do unvoiced segments, then the sound carrier is actually eliminated at a moment in time, but that limits the loudness because vowels which have the carrier built in there are intrinsically louder than consonants that don't have the carrier. And so what you have to do is limit the loudness on the vowels in order to keep the loudness of the unvoiced segments the same. As a result, speech only can cause a laryngeal contracture, and I'll say more about that. Some acoustic evidence for speech only problem is we did a study in Denver of teachers for about 10 years and measured the dosimetry. And while the dosimetry is measuring basically how often they vibrate their vocal folds. But we found that there's a very limited voice range profile among teachers. Let me show you that. If Eric Hunter is on board, he was part of creating this diagram. We worked together at the time. But you can see here, this is for males. The situation for females is almost the same, except you move everything up by about 50 hertz or so. But here you see that these teachers, 70% of the time that they vocalized in class, is this outline right here, was between 100 and 200 hertz. Males have a voice range profile that takes you all the way up to 500 hertz or higher. So this entire yellow region is never accessed by speech only. And so we're working in a very, very contracted space all the time. Also, as I said already, that speech invites a low fundamental frequency. Why? Because the formants need to be sampled with harmonics being closely spaced. And when you want harmonics closely spaced, then you have to put the fundamental way down. Otherwise, you don't get clarity of the vowel. And there's also less source filter interaction when strong harmonics are below the formants, or less chance for source instability. So let's look at one more time as what we call the source filter theory. If our source spectrum has all of these harmonics and our vocal tract has these resonances, in order to keep the modulation, which is moving the formants around, apart from the carrier, then we want this first formant or the second and all these high enough so that the strongest harmonics, namely the fundamental and maybe the second harmonic, do not enter this region all that much. So for conversational speech, that's kind of the requirement. And again, with the speech-only problem comes the fact that the muscles operate in a contracted region in speech. Muscle length is rarely an optimal sarcomere length, and the agonist-antagonist pairs of the muscles are often not well balanced in activation. This is what's known as a muscle activation plot, where you show thyroretinoid muscle activity horizontally and cricothyroid activity vertically, and speech is almost guaranteed always to be in the lower left quadrant here, whereas singing and calling up in the higher quadrants here. And the frequencies that are represented here are shown here, ranging between 98 hertz and 440 hertz. So if our larynx is speech only, we never get into this region here, and we don't exercise the larynx in the way that we could. Comparing that to chimpanzee voice range profile, it's hard to get. You can't put them in front of a piano and say, here, sing this note. But on the other hand, you can go out into the woods and you can listen to their sounds, and they have sort of the intimate sound range, which is like our conversation with speech. And there's basically sounds like hoo, hoo, ha, ha, hoo, hoo. But then they also have the long distance calls, and they're very rough often. Ah! But in these rough long distance calls, they do exercise the muscles of their larynx in a way they would not if they were only in intimate situations. Almost done here. Vocal fry is something that was discussed almost daily a few years ago, maybe 2 or 3 years ago. Let me explain that in terms of the Carrier-Modulation principle. Vocal fry provides, yes, a dense fundamental frequency spectrum. That should be good for getting a lot of harmonics into the formant regions. But, and there's a big but the carrier frequency begins to approximate the modulation frequency, because in vocal fry, the carrier frequency is generally less than 70 hertz. But if you look at the phoneme rate in speech, it is generally 10 hertz or higher. So you don't have the 10-to-1 ratio anymore that we're looking for to keep apart the modulation from the carrier. And when they mix together, then you don't know what the message is anymore, because the message has to be the modulation only, not the carrier. So vocal fry promotes keeping some laryngeal muscles like the CT in a deactivated state, probably also not good. But I'll put another but with it. Maybe over time, fry can become fashionable if the roughness is no longer an annoyance and the production is stable. But I'll put a big question mark behind that for reasons given above. So in conclusion, sound and light are carriers that transmit creative intelligence. With our 5 senses, we detect only a tiny portion of this information and the intelligence that passes through us constantly all day long. Intelligence vocalization expands future options with greater ranges in pitch, loudness, and timbre. Let me make sure that we get this right, because this relates right back to what Wissner-Gross was talking about. The way you want to create more intelligence is to create more options for the future, more different cases of how to organize things. You want one organization of this type with the same material and another organization of another type with the same material and so forth. And so if you create many, many options, diversity, if you will. I'm so saddened by the fact that in schools nowadays, the diversity always means just diversity of skin color. It doesn't mean diversity of thought, diversity of outcome, diversity of effort, diversity of reward. All of these things are part of increasing the intelligence of the universe. So when you talk to your DEI people, tell them that we want to widen what is meant by diversity if we're going to increase the intelligence of the world that we live in. And a robust and stable carrier voicing is needed for effective vocal communication. And here are some things for you to ponder. That's the last slide I have here. Do you gain your intelligence only from existing intelligence around you, which is very much what we do a lot. We take kids out into nature and they look at trees and they look at structures and so forth, and they gain intelligence from the intelligence that exists right there in front of them. And we gain some intelligence from social media and from our professors. Or an alternative to that, do you access the cosmic intelligence that I referred to and is my belief? And I'll state that clearly. That intelligence reservoir through meditation, inspiration, prayer, long and deep thought. And if we look at people that we adore in our history, like Albert Einstein and Beethoven and Gandhi, these are people who spent a lot of time in solitude, thinking, and connecting to the virgin intelligence that has not yet been on Earth. And that is how they create the major changes that can occur. If we spend all our time on Facebook and we always just look around us in short circles, we do gain some intelligence, but it's never anything new. It's just what already exists. So that leads me to whatever time we have left for discussion.